All right, welcome back, everybody. So this is section 4.4. Again, we're going to do, for the folks playing along at home, we're going to do a test next Monday and Tuesday of next week. We only have this section 4.4 to do, and then we will review on Wednesday, Thursday, Friday, test Monday, Tuesday. Okay. All right, section 4.4, indeterminate forms and L'Hopital's rule. L'Hospital's rule.
I was gonna say that.
I know. That's how I always remember it. L'Hospital's rule. All right. Think back to something like this. Okay, think back to that function. F of x is equal to ln of x over x minus 1. I have the natural log of x divided by x minus 1. So suppose we wanted to try to take that limit. Suppose we wanted to try to take that limit. The limit of x as x approaches 1 to ln of x over x minus 1. I mean, the best route to take would be direct substitution, correct? The best route to take would be direct substitution. Can I do direct substitution? Why not? Because it would make a 0 in the denominator, and that's what we call an indeterminate form. When something is not computable like that. Now, back in semester 1, back in, what was that, chapter 2, in chapter 1? Back then, we said, okay, maybe there would be a way to reduce it down. Some way to reduce it down, maybe we factor and it reduces out, and then we can plug in 1 eventually. Does that work in this case? No. So I would be stuck here. I cannot actually compute this limit based on reducing it down in any sort of way, any sort of algebraic way. I can't directly substitute 1 into x. So there's got to be something else I can do. Okay? In computing this limit, we can't apply just plugging it in, and we can't take the limit of each quotient because the denominator is equal to 0. So what we have to do, so this is what, again, what's called an indeterminate form, where if I plug in the top and the bottom, I get a 0 over a 0, right? If I say I'm going to plug 1 in for ln of x is 0. Ln of 1 is 0. If I plug 1 in for the denominator, I get 1 minus 1 is 0. It's an indeterminate form of the type 0 over 0. Other indeterminate forms are when we have infinity over infinity, right? Infinity over infinity, that's an indeterminate form. One that you cannot easily compute. Okay, that's really what an indeterminate form is. Ones that you cannot easily compute. Like, for example, ones that we could do back in, it says chapter 2. Back in chapter 2 is something like this, where I have like an x squared minus x over an x squared minus 1. Like, I can't do direct substitution because the top and the bottom would both turn into 0, and it doesn't make sense. Can't easily compute that. So what I can do is factor out the x in the numerator, factor the difference of squares in the denominator, and x minus 1 eventually cancels out, leaving an x over x plus 1, which I can directly substitute. Would be x is equal to 1/2. But that whole ln of x over x minus 1, I cannot directly substitute. So what do we do with something like that? We have this thing called L'Hopital's rule. It says that if it's an indeterminate form, okay, suppose that f and g are differentiable and g prime of x is not equal to 0. So when I take the derivative of the bottom, it doesn't turn into 0. Suppose f and g are differentiable and g prime is not 0 on an open interval. Suppose that if I take the limit as x approaches a of f of x is equal to 0 and g of x is equal to 0. So the top and the bottom function are both going to 0. Or the top and the bottom function both go to infinity. Okay? Either the top and the bottom function both go to 0, or the top and the bottom function both go to infinity. Those are indeterminate forms type 0 over 0 or infinity over infinity. Then L'Hopital's rule says that if you have the limit as x approaches a, if it's an indeterminate form, you can actually find the derivative of the numerator and then the derivative of the denominator separately, and then take the limit of that. The limit of the function, the quotient of the function, is equal to the limit of the quotient of the derivative. Let me say that again. The limit of the quotient of the function, the limit as x approaches a of f of x divided by g of x, is actually equal to the limit as x approaches a of f prime of x divided by g prime of x, which is a very powerful statement. Finding the derivative of a function reduces it down a lot. So if we can reduce it down to find the derivative, and then reduce it, once I reduce it down, find the limit of that reduced down function, it's usually a lot easier to do. Okay. Special notes here. L'Hopital's rule says that the limit of a quotient of the function is equal to the limit of the quotient of the derivatives, provided that the given conditions are satisfied. It's extremely important that you check to make sure that the conditions, the hypotheses are satisfied. It's got to be an indeterminate form. If it's not an indeterminate form, L'Hopital's rule doesn't hold, it doesn't exist. Okay? You can't use it unless it's an indeterminate. Special note for 2, L'Hopital's rule is also valid for one-sided limits. Okay, you can find the limit as x approaches a from the positive direction or as x approaches a from the negative direction. Okay, depending upon the domain of the original. Like, if you're thinking about natural log of x, can it approach 0 from the negatives? No, because I can't plug in negatives into ln of x. I can't plug negatives into any logarithmic function, so therefore it would have to go from the right side. I would have to only approach 0 from the right side. But L'Hopital's rule would still hold because it still works with one-sided limits. So note 3 just kind of proves L'Hopital's rule. Basically, for when f of a is equal to f of g is equal to 0, when f of a and f and g of a are both 0. Basically, it's saying that, showing here that f, if you want to take the limit, it's equal to the limit of the original. And also, again, just like everything, if you wanted to see the proof of any of this stuff, it's all in the book. I just kind of edited it out for you because I don't think you guys really care about that. Okay, so let's actually find this limit now. Okay, this is the one we were thinking about before, the ln of x over x minus 1. Let's actually find this limit using L'Hopital's rule. Now, first thing that we want to do is make sure that it holds. Make sure that the hypotheses are, that I have the conditions met. Like if I took, the limit of, as x approaches 1 of ln of x, what is that? Well, if I plug in 1 directly for x, what is ln of 1? 0. Right, ln of 1 is 0. Right, so log base e of 1 is equal to what? So e to the what power is 1? Anything to the 0 power is 1. Okay, so let's find the limit as x approaches 1 of x minus 1. Well, that one's a little bit easier. That is just included. So this is an indeterminate of the form 0 over 0. Okay, if I plugged it in, I would get a 0 divided by a 0. So that means that I can use L'Hopital's rule. So that means I can say that the limit as x approaches 1, I'm just rewriting, of ln of x over x minus 1 is equal to the limit as x approaches 1 of the derivatives. Well, what's the derivative of ln of x? 1 over x. What's the derivative of x minus 1? 1. Oh man, that makes it a lot easier. So that's like saying the limit as x approaches 1 of 1 over x, of 1 over x. And that we can directly substitute. 1 over 1 is 1. See, it simplifies it a great deal when you can find the derivative. You find the derivative and it's a lot easier to compute. You can actually use L'Hopital's rule continuously, right? If you use L'Hopital's rule and then you get another indeterminate form back out again, you can actually use it again, and then again, and then again, until you get something that you can compute. It's convenient like that. It doesn't just work once, it works continuously. Let's try another one. The limit as x approaches infinity of e to the x over x squared. Limit as x approaches infinity of e to the x over x squared. You know, does L'Hopital's rule hold here? Well, as x approaches infinity of e to the x, well, if I plug infinity, isn't it just going to keep getting bigger and bigger and bigger? Yeah. Same thing here. X squared is infinity as well. So this is an indeterminate form of infinity over infinity. I don't know which one is growing faster or slower than the next, right? E to the x or x squared. So I can't tell if I find the quotient of them where it's actually going to be at. But what I can do is find the derivative, because now I know if I've got indeterminate forms, I can say the limit as x approaches infinity of e to the x over x squared is equal to the limit, keeping the same going to, of the derivatives. Now be careful here. I always have a lot of people trying to say, I've got to use the quotient rule because it's a fraction. You don't have to use the quotient rule. All you're doing is finding the derivative of the top and then the derivative of the bottom. You instinctually want to use the quotient rule because you see a fraction there, but don't do that. You don't have to do that. And you have a question?
So you know how the limit of f and x for the infinity indeterminate, does it have to be the same sign on the infinity?
No, because it could be positive or negative. You could have one positive, one negative. They don't like cancel out or anything. It would still be indeterminate. You wouldn't be able to tell what it was if they were both going to infinity, one direction, the other. Okay, so now let's find the derivatives. Well, what's the derivative of e to the x? E to the x. What's the derivative of x squared? What? I didn't say all these people. Yeah, you did. Yeah. I didn't teach you. Shut up, Christian. All right. Now, if I plug infinity in, what's going to happen again? Like, think about the limit. The limit as x goes to infinity of e to the x. What is it still? Think about this. The limit as x goes to infinity of 2x. So I still have another indeterminate form. I still have infinite over infinite. Well, in this case, I can use, since it's another indeterminate form, I can use L'Hopital's rule again. All right. So that means I've got the limit as x goes to infinity of derivative of e to the x, e to the x, over now just 2. And that I can compute. Because now it's no longer infinity over infinity. What is it? It's infinity over, which is still just infinity. Even though it's divided by 2, it's still going to increase all, to infinity and So what do we see here? You can use L'Hopital's rule again and again if you need to. You can use it 3 times if you wanted to. There's no limit to it. Yeah.
Why can't you find that e to the x equals infinity and x squared for, like, if the bottom part is just what matters, like the fraction part?
They both need to go to infinity. They both need to go to infinity. Because if it was like 2 over infinity, it would go to 0, right? So they needed to be infinite over infinite for it to be an indeterminate form. If it was 2 over infinity, it would just end up going to 0. Because 2 over a big number is just, essentially 0. Does that make sense? Yeah. Okay, let's take a look at another one. I'll tell you this right now. I did the assignment last night. It usually takes me like a couple sittings to do the assignment. I did it all in one sitting in about an hour, and it wasn't too bad. It's a lot, but I show a lot of work on these. So, and I try to use really good handwriting, because my handwriting is normally really bad. So it usually takes me a while. This time, it didn't take me too long. It's a lot of algebraic, just use the rule, use the rule, use the rule, use the rule. Make sure it's in determinate form, but use the rule over and over. I know, the last homework was like, page.
Why did you make us do
Why?
You know, I don't know, obviously it didn't work.
Yeah, no, you didn't.
I'm just kidding, sorry, that was sorry about that, sorry. All right, here we go. Let's check to make sure L'Hopital's rule holds here. The limit as x approaches infinity of ln of x. Okay, what happens if I get increasingly bigger and bigger and bigger? It keeps getting bigger and bigger and bigger. If I keep going on to the right side, it goes to infinity. Oh, I want to take that. And I do the same thing over here. The limit as x goes to infinity of the square root of x. Still, even though I'm taking the square root of it, it's still going to keep going on forever and to the right. Forever, ever up. So I see that this again is an indeterminate form, infinity over infinity. So let's use L'Hopital's rule here. Limit as x goes to infinity of ln of x over the square root of x. So that would be like saying 1 over x, oops, sorry, forgot my limit. Limit as x goes to infinity of, now we differentiate top and bottom, 1 over x. And now, remember that, isn't this x to the 1/2? Okay. So this is like saying 1/2 x to the negative 1/2. Okay, which is really like saying, forgive me for not writing the limit again, 1 over x divided by 1 over, okay, hold on. I gotta think with it. Let's change it to multiplying. Times, because since it was negative, 1 over 2 How did I get there? Well, because this, isn't this 1 over x divided by 1 over, oh, I just wrote the same thing.
So the one on top is the keep change flippy thing?
Keeps change flippy thing.
Yeah, so it should be 2x times the square root of x over 1, right?
What?
Huh?
No, I'm just trying to hang up.
Because-
Square root of x.
Because,
That came out of nowhere.
What is this, anyway?
You turned your rate.
yeah.
Yeah. What should it be?
It should be 2 square
So now
root
you
of
just
x
flip
over
it.
one.
So now we just flip it, yeah. So 1 over x times 2 square root of x
Over 1.
over 1, yep. Yeah, that was my next step.
Oh, so that's the next step. So it's not replacing the one. That's not the 1 over the 1 over.
Where did you get 1 on the top?
Okay, give me.
Where did you get the 1 on the top? Why is there an extra 1?
Why is there an extra 1? Because of this right here.
But I thought it was one separate problem.
No.
You do.
Yeah, it is.
Yeah,
It should just be 1 over
Yeah.
2 square root of x.
1 over 2 square root.
Not 1 over.
Because that's 1/2 times x negative 1.
No, but it's 2, it ends up being 2 square root of x over 1. Like all in total in the end.
Yeah.
Yeah,
But how do you have an extra 1?
Yeah, there's the 1 on top.
You have a 1 on top and then you have another
1.
1.
On line above
Because
it.
the negative one has to take it back
Yeah.
under.
Yeah,
Yeah, from the top.
One of the numerator.
I just accept whatever you say without.
Yeah, me too. Because one
I have no
over
question.
times one over.
Sorry, hold on.
Yeah, all you have to do is.
Oh my God. Okay, sorry. I know, really, no.
We have the same answer.
Just talk about your job.
Yeah.
So do we all agree that this is where it gets to, right?
Yes.
Okay. I don't know. So it ends up being 2 radical x over x. Okay, just multiplying through. And then think about this. So 2 radical x is 2 times x to the 1/2 power. Subtract the exponents. So 2x to the negative 1/2. So this ends up being 2 over square root of x.
And then do we put the infinity in?
Well, and now we evaluate the limit. Yep. Now what happens when we evaluate that limit? It keeps getting smaller and smaller and smaller number, right? The number keeps getting smaller and smaller and smaller because if I have 2 over a big number, even though it's square rooted in the bottom, it's still going to keep getting bigger and bigger and bigger, right? So even though it's square rooted in the bottom, it's going to end up being like 2 over infinity. So 2 over a really big number is essentially what?
0.
So my answer is 0. You'll find the ones in the homework are a lot more like they're polynomial ones, right? Which are easier to find the derivative of. But, is this the one that I wanted to do? Okay.
Is there a polynomial example we can do real quick? Or is there not?
Not in my notes, but I can. Yeah, let's do a polynomial example real quick, because that would be. Let me pull one out of the book real quick. Chapter 4. Oh no, sorry. I want this chapter 4. There we go. All right. Let's do. Let's take a look at. We have to do 11. No, we don't have to do 11. That's a good example that we could do. I'm not gonna do one of your homework.
It's all going to be something over something else. Right,
Because those are usually indeterminate forms.
Okay.
There are some at the very end when we talk about subtraction or quotient or product of indeterminate forms.
Okay.
So let's take it, but the ones in the homework are mostly just one over the other with the fraction. And again, why is this an indeterminate form? Because if you plug in 1, what's going to happen? The top is going to go, the bottom is going to go to 0, right? And the top actually as well is going to go to 0. So this is an indeterminate form of 0 over 0. Could I possibly try to reduce it down like with algebra? Yes, but I don't know. I don't really want to do a difference of cubes. You're going to find that L'Hopital's rule is actually a lot easier to do. So the limit as x approaches 1 would be 3x squared minus 4x over 3x squared. Everybody follow me there?
Yeah.
I mean, I guess I should have written out that the limit as x approaches 1 of x to the 0 minus 2x squared plus 1 equals 0. The limit as x approaches 1 of x to the 3rd minus 1 equals 0, so that we know that L'Hopital's rule actually does hold. What's going to happen here, though? Can I plug in 1?
It's still indeterminate, right?
If I tried to plug in 0, yes. But I want to go to 1. So this is gonna be 3 minus 4 over 3.
Why?
So the total limit's gonna go to negative 1/3. You see how that works? See, the easier it is to take the derivatives, the easier L'Hopital's rule is. I'll tell you that the homework is mainly polynomials. There are some a little bit more difficult ones, like some with trig and some with like natural logs and stuff like that. But we'll talk a little bit more about those tomorrow. Does that sound good?
Yes, that is it.
Okay.
Not today.
Not today. Not today.